Okay, hi everyone. Thank you for coming to this webinar. So today, Holly Judge from EPCC will be giving a talk about how MPI and OpenMP perform on a variety of common applications used on ARCHER2. So Holly, take it away when you're ready.
Hello everyone. So let me just share my slides. So I'm Holly, I'm from the EPCC, and I'm going to give an overview of the performance of MPI plus OpenMP on ARCHER2. So this is based on some work that I originally did for the Cray user group conference back in May. So yeah, what about our partners, part of the UKRI, EPCC, which is where I'm from, the University of Edinburgh and HPE that provide ARCHER2. So here's a bit of an introduction about what I'm going to be talking about today. So typically HPC applications are run with MPI. So this means you have many message passing. You typically spawn a single process per core when you run the application. However, for some applications, you have the option to run MPI plus OpenMP. This uses a combination of processes and threads. And this can be done as an alternative to MPI. This might achieve better performance than MPI, but this depends, and there are a lot of factors that this can depend on. This is some of the stuff I'm going to be talking about today, and I'm going to actually present results. So using MPI plus OpenMP might be good for taking advantage of the resources in ARCHER2 nodes. ARCHER2 has 128 cores per node, whereas its predecessor ARCHER had only 24 cores per node. So this is quite a different balance of having a lot more cores on a node. And then using MPI plus OpenMP may take better advantage of this than just using MPI on its own. So yeah, basically the goal of this is to find out when can we get good performance with MPI plus OpenMP. So what kind of applications typically benefit from it? What sort of systems and test cases within these? And then how many threads per process is typically gives you good performance. So here's an outline of what I'll cover today. I'll go over ARCHER2 and some specifics of the hardware and how this relates to MPI plus OpenMP. Then I'll give a bit of an overview of MPI plus OpenMP and how it's different to MPI, and also how it can be used on ARCHER2. I'll then cover my performance investigation of MPI plus OpenMP on ARCHER2. So I've covered some different applications and then different test cases within these. And then finally, I'll end with a bit about how users might be able to benefit from using MPI plus OpenMP on ARCHER2. So ARCHER2, which we're familiar with, it's the UK National Service for Scientific Research. It's a HPEX system. It has 5,860 nodes, and this amounts to just over 750,000 cores. It uses AMD EPIC processors, and the slingshot is the HPE, and the interconnect is the HPE slingshot interconnect. Taking a look at the node level architecture of ARCHER2, so each node is comprised of two 64-core AMD EPIC processors, which amounts to 128 cores per node. There are 256 gigabytes of memory per standard node and 512 on a high memory node. And each node has 8 non-uniform memory access regions. So these are 16 cores each. And then within this, there are groups of 4 cores which share L3 cache. So ARCHER2 nodes have 256 gigabytes of memory, and there are 128 cores. So if you run with MPI, you use 1 process per core, you end up with roughly 2 gigabytes of memory per process. This is slightly less than there was on ARCHER, where there was 2.6 gigabytes per process. But this amount of memory per process can actually not be enough for some memory-intensive applications. And what you we've seen is lots of applications can get out of memory errors. And as a solution to this, we suggest underpopulation, so using less processors than the number of cores. So typically you'll use 64 processors per node and then get double the memory per process. And also, if you use one process per core, this can have some negative effects on the MPI communications. So basically you can end up with a lot of processes sending messages, and then this can increase the overhead of MPI communications. So using MPI plus OpenMP, where you have less processes per node and multiple threads per process, can maybe help here. So this is what it looks like in practice. For MPI, each core has one process or task spawned to it, and then it has its own distinct memory space per process. And then between these processes, communication between them takes place via messages. On ARCHER2, with 128 cores per node, you set task per node equals 128. You will use one OMP thread, and then you end up with 2 gigabytes of, roughly 2 gigabytes of memory per task. With MPI plus OpenMP, you're using a mixture of threads and processes spawned onto the cores. So you'll typically have groups of threads within a memory region, so across the same memory region, and then at least one process per memory region, because you need message passing between memory regions. This is because you don't want threads spanning multiple memory regions, because this is really bad for the performance when you're accessing memory. And then, yeah, you end up with less processes and per node, and then this means you end up with more memory per process, as if you were underpopulating, and this memory is shared between the multiple threads. You also can end up with less copies of data on a node, so if you've got a memory-intensive application, this can be a massive benefit. Less processes, again, can also mean less inter-node messages, and particularly if you're doing a lot of collective communications, this can help reduce the communications overhead. So, yeah, MPI plus OpenMP is typically implemented in quite a few HPC applications. However, it's maybe not always more performant than using a single thread, like pure MPI. So what you actually require is good OpenMP coverage within the code. Typically, what will happen is developers will take an MPI code and then sequentially add bits of OpenMP to it. But this means when you're outside of an OpenMP parallel region, you're only running on, you're basically not utilizing the power of the cores. So in this diagram here, you're only using the, you're restricted to the head process, and you're not using the, utilizing the cores which the threads are run on. So basically you need good OpenMP coverage within the code in order for the performance to be good. And then the number of threads per process needs to be then tuned to the use case, so the application itself and also the machine. I mean, in this case, I focused on ARCHER2 in particular. And then you need to be aware of the underlying node structure. So you need to know where, how big your memory region is, and be careful not to spawn multiple threads across multiple memory regions. So how does this look like on ARCHER2? So I've got here is an example job script for running MPI plus OpenMP on ARCHER2. So this example uses 16 threads per process. So you can see OMP number of threads has been set to 16. And then this is set to the same as CPUs per task, because you need to ensure that each thread is spawned onto a core and that the placement is correct. Yeah, and so in this case as well, task per node is set to 8. This is because there are 128 cores per node on ARCHER2, and then when you take this and the number of tasks and the number of threads, this equals 128. So you ensure that the node is fully populated with both processes and threads. Because of the NUMA structure on ARCHER2, and there's the fact that there's 16 cores per NUMA region. This restricts you to using no more than 16 threads, really, because of going beyond this, you'll typically get bad performance. And because you need this to be the threads to sit nicely across the NUMA regions, you can only really use multiples of 16. So on ARCHER2, using 1, 2, 4, 8, or 16 threads per process are sensible values. Okay, so now I'll come on to my results. My investigation. So this is a graph showing the application usage on ARCHER2. So within my investigation, I typically want to look at codes that are commonly used and codes that also have MPI+OpenMP within them, in order to be able to give a good representation of what applications are used on the system. Yeah, this is the usage in terms of core hours on ARCHER2 for June, so last month. You can see here VASP is the most used application, and then there's others, Cbdk, GROMACS, CASTEP, and LAMMPS. So these are typically quantum chemistry codes and also classical MD codes. So here are the applications that I chose to investigate. So I wanted to focus on well-used applications, so I picked some from the most used applications on ARCHER2. Those applications which are essentially supported by the ARCHER2 team, because we have everything available and all the build instructions set up, applications which are MPI and OpenMP enabled. For each of these applications, I've selected different test cases for different scales, so to be able to run on a few nodes and then many nodes going up to a few hundred nodes. So I focused on Cbdk, LAMMPS, CASTEP, Quantum EPRESSO, and GROMACS. I've put the results on this GitHub repository, and yeah, the performance I compared typically using 1, so kind of like pure MPI, 2, 4, 8, and 16 threads per MPI process. So a bit more about the applications that I focused on. I looked at CASTEP, which is density functional theory software package, and it does electronic structure calculations using plane waves. Focused on version 20.11, and you can see the environment that I used to build it. So GCC version, I used MKL and MPitch and FFTW versions. CASTEP has OpenMP within its FFTW routine and then its linear algebra libraries. Cbdk I also looked at, and this is a quantum chemistry and solid state physics package and uses mixed plane waves of Gaussians with Gaussians. I looked at version 8.1, and then you can see the software I used to build it as well. So Cbdk has OpenMP within its real space to plane wave transfer, its collocate and integrate routines, FFTW, linear algebra libraries, and more, I believe. Also looked at GROMACS, which does classical molecular dynamics of biological systems, and looked at version 2021.3, and this has OpenMP within its particle mesh Ewald calculations. And looked at LAMMPS, so another classical MD code, and this time more focused on materials modeling. I looked at the January 2022 version, and LAMMPS typically has OpenMP within its pair interactions and FFTW routines. And then finally, I looked at Quantum EPRESSO, which does electronic structure calculations with plane waves. Looked at version 6.8, and this has OpenMP within its integrals, point evaluation functionals, FFTW, and linear algebra libraries. And then for each of these applications, I looked at different test cases. So for CASTEP, there's a DNA system, which is meant to be a large sort of memory and compute intensive system. And then AL3x3, which is a smaller system. Cbdk, focused on H2O64, which is a kind of small water, very small water system, which uses the local density approximation. And then H2O512, which is just a larger water system with the same setup, but 512 molecules. And then LHIFX system. So this is a lithium hydride crystal. This uses the ARCHER2 exchange, and this is meant to be memory and compute intensive. For GROMACS, focused on 2 MD simulations of 1.4 million atoms and 3 million atoms, and then a larger MD simulation which has 12 million atoms. And then for LAMMPS, I've got the same MD simulation as for GROMACS with 3 million atoms. For Quantum EPRESSO, I looked at a graphene iridium system which does an SCF calculation, uses 4K points, and then a carbon nanotube, which is again a larger, more intensive system. Okay, so here's the results. So these are the results for the Cbdk, the small water benchmark. So this is a very small system and it doesn't scale very well, possibly not even beyond a node. But you can see here in this graph of the runtime versus nodes, the benefit of using multiple threads per process. So in this case, even on one node, using 2 threads per process gives a much faster runtime than a single thread. And this, trend is followed as you scale out. The runtime in this calculation is dominated by MPI all-to-all, and this contributes more and more as you start running across multiple nodes. You can see here in this little table at the runtime of MPI all-to-all on 1 thread and 4 threads. And you can see as you start to use more and more nodes, the runtime blows up massively. But on 4 threads, this effect is a lot reduced. And then comparing one node, even on one node, the runtime of MPI all-to-all is a lot faster on 4 threads. So yeah, this really dominates this calculation. And then using MPI+OpenMP reduces the runtime of the communications. So this is due to message aggregation, basically reducing the number of off-node messages. And then looking at the slightly larger version of the Cbdk benchmark, so this effect is again present. So you can see if you use more threads per process, you can scale out even further beyond the single-threaded version. So in this case, using 2 or 4 threads per process reduces the runtime compared to 1 thread, and then this effect is way more pronounced as you get to using more nodes. Again, this is due to the reduction in communications overhead. If you look at the performance of this, so this is comparing the performance of 1 thread and 2 threads per process, which was the best configuration for this result. You can see that even on 4 nodes, using 1 thread per process gives a parallel efficiency of about 60%, whereas 2 threads per process, this is 70%. Now looking at the larger, more intensive Cbdk benchmark. So this is a hybrid calculation of ARCHER2 exchange. So this is more memory and compute intensive. In this case, using 4 or 8 threads per process gives the best performance. So even on 32 nodes here, 4 or 8 threads per process has a faster runtime than using a single thread. And then again, as you go up in nodes, this effect is a lot more. So the performance of 1 thread gets a lot worse. And then the performance of when using multiple threads gets better. So yeah, the increase in performance of multiple threads in this case is slightly less significant, as this is dominated more by computation of the integrals rather than communications. And then here's another performance comparison for this one. So this is 8 threads versus 1 thread, and you can see a massive difference in the performance. So yeah, taking some numbers, on 128 nodes for 1 thread per process, the parallel efficiency is 52%, whereas on 8 threads it's up to 68. And then if you go beyond this, on 256 nodes, you see really poor parallel efficiency on 1 thread per process, but this is a bit better on 8 threads per process, so it's 49%. So moving on to CASTEP, so this is the DNA benchmark. This is a larger sort of memory intensive calculation. So on 32 and 64 nodes, you can see that the performance here is better with 1 thread. This is performance rather than runtime, so a bigger value is better. So yeah, on 32 and 64 nodes, 1 thread is better. However, when you start to scale out, you can see on 128 and 256, using 2 threads per process or 4 threads yields better performance. Again, in CASTEP, MPI collectives seem to dominate the runtime. So this is due to the effect of reducing the communications overhead with multiple threads. And then this is the smaller CASTEP benchmark. So this is the AL 3x3. This is just doing a single point energy calculation. So this graph shows the time. So a bigger value is worse. So there's not that much difference here on comparing, 1 thread to multiple threads, particularly at lower node counts on 1 and 2 nodes. It's all quite similar. But then, yeah, once you start using more nodes, using multiple threads per process, so using MPI plus OpenMP starts to improve the performance. Okay, so on to GROMACS. So these are 2 molecular dynamics simulations of 1.4 million atoms and 3 million atoms. So these will run on scale up to different amounts. So yeah, you can see the 3 million atom scales out to more nodes. So for GROMACS, you don't really see that much benefit from using multiple threads. So yeah, looking at these, the performance is pretty much up until you start to reach the scaling limit, and the performance is always better on a single thread. But yeah, once you get out to the point where the code kind of stops scaling, it helps a little bit. So you can see here on 16 and 32 nodes with the 1.4 million atom case, there's a bit of performance benefit for using 2 or 4 threads per process. And then with the 3 million atom case, yeah, again, sort of 32 nodes beyond, you start to see a benefit from MPI plus OpenMP. So this is only because the timing of the PME, the particle mesh EWOLD communications, starts to become significant at scale, and then using MPI plus OpenMP can help with this. But the performance is not good for more than 4 threads. So this represents the size of the L3 cache in ARCHER2. So going beyond 4 threads, you start to have threads across multiple, going beyond the L3 cache, so it starts to hamper the performance. And it's typical for classical MD calculations, which aren't that memory intensive. And then this is a slightly larger GROMACS MD simulation. So this is a 12 million atom one. again, see kind of a similar thing. So yeah, there's not much benefit from using MPI plus OpenMP for 1 to 16 nodes at the lower end of the scale, but when you start to get beyond or at the scaling limit, using multiple threads per process starts to give you better performance. So here, using 4 threads per process on 32 and 64 nodes. Again, it really starts to tail off on 8 threads due to the cache effects. Okay, and then moving on to LAMMPS. So this is the same 3 million atom benchmark. Kind of see a similar picture here, but the performance is, you can see the performance is a lot worse on multiple threads, basically up until you get to using large node counts. So only once you get to 64 and 128 nodes does it actually have any benefit. So this is actually due to a slight issue with the I/O in LAMMPS. So on many nodes, there was a problem with write speed. So using MPI plus OpenMP actually reduces the number of processes, and then that helps reduce the I/O overhead. But this was actually due to an issue in the OFI protocol. So switching to UCX can actually help with this. So yeah, this is something kind of following up on. And then for Quantum Espresso, so this is the graphene iridium benchmark. So Quantum Espresso seems to be quite memory intensive for the calculations that I've run. So on a single node, this calculation fails with an out-of-memory error. And then when you start running it on, well, it runs on 2 nodes, but it doesn't work on a single thread. So there's actually not enough memory per process for a single thread on 2 nodes. So I don't have results here for a single thread. So yeah, here using MPI plus OpenMP doesn't benefit the performance of the calculation. So yeah, the runtime is better for a single thread, but it can help with the memory requirements. So you can see that it actually runs on 2 threads where it wouldn't run on a single thread. For the larger Quantum Espresso benchmark, so this one has a lot higher memory requirements than the last one. It runs out of memory on 1 and 2 nodes, and then on 4 nodes, it runs on 2 threads, but not on 1 thread, again, due to the lack of memory. So yeah, using MPI plus OpenMP can help with the memory requirements here and prevent the out-of-memory errors. So you'll see that it increases the memory per process, and then this allows, so then this improves the performance on 8 and 16 nodes. So here in this table, I've given the runtime on 8 nodes. You can see, so if you use MPI, the runtime's MPI alone with 1 thread and 128 processes per node. The runtime is quite poor. And then if you switch to using underpopulation, so 64 processes per node, but without any threading, this improves the runtime a lot. So this calculation is quite memory limited and obviously benefits from having more available memory. But then again, if you use multi-threading, so use 2 threads and 64 processor nodes, this then benefits the runtime as well. So this can improve the performance. So to summarize the results, so the quantum chemistry codes, such as Cbdk and CASTEP, are able to benefit from MPI plus OpenMP in general. These codes seem to be quite dominated by MPI collectives, and then using MPI plus OpenMP helps reduce the number of messages and reduces the communication overhead. So it's got good benefits here. From Quantum Espresso, for Quantum Espresso, it allows more memory per process. So this is a memory for memory intensive calculations. When you have to underpopulate, it can be useful in this case. But for classical MD codes such as GROMACS and LAMMPS, it doesn't seem to benefit that much. So it can improve the performance, but only really at the scaling limit. Okay, so the last thing I'll talk about for the next sort of 5 minutes is how users can maybe benefit from MPI plus OpenMP on ARCHER2 and sort of what steps you should maybe look at. So first thing is check, if your application is MPI plus OpenMP enabled. So I've obviously covered some that use MPI plus OpenMP, but there are others as well on the system. So to improve the performance, so if you've got an application which is typically dominated by MPI collectives, using MPI plus OpenMP might help in this case. So this is what I've seen from Cbdk and CASTEP, and if you're running one of these codes, I'd suggest you look into using MPI plus OpenMP. So yeah, this reduces the overhead of MPI communications, and yeah, at the scaling limit, you can improve the performance, and even before that as well. And if you have out of memory errors, so if you've got a memory intensive calculation where you run out of memory and you find that you're having to underpopulate the number of processes on the node in order for it to run, so setting tasks on node to 64 rather than 128. So yeah, if you're in that case, you're reducing the number of processes of a node, but then you can also use threading as well. So maybe you can benefit in that way. So yeah, you're allowing more memory per process with MPI plus OpenMP, and then yeah, having threads on top of that may also help with the performance a bit. So to go away and use MPI plus OpenMP, so you really have to test most of the time. I mean, yeah, I have some results which suggest some values might work on some applications, but you really have to test your own particular application and your own particular test case, whatever scale you're running on as well. So yeah, you need to go away and maybe do some measurement. So yeah, test the different numbers of threads per process. But usually I've seen 2 or 4 threads. Usually it gives you good performance if it's going to. And yeah, make sure that the thread placement is correct and that the processes and threads fully populate the node. Your best value for threads per process is going to vary on lots of things, such as your application, what particular problem you're running, and the number of nodes/cores that you're using. And if you're underpopulating for memory reasons, then you may as well try using multiple threads if you're already having to reduce the number of tasks. Okay, so to conclude, so yeah, on ARCHER2 applications can benefit from MPI plus OpenMP. This is what I've seen. There are performance benefits. So usually when you've got applications that are very communications heavy, this can help when you're running on multiple nodes and the MPI comms start to dominate. This is because the messages get aggregated and you're sending less internode messages. In this case, using 2 or 4 threads per process has typically been shown to be good. It can also help with memory requirements, so yeah, allowing more memory per process and less copies of data on a node. This is particularly important for memory-limited applications or memory-limited test cases. It might be less useful for classical MD codes, so from what I'm seeing, it doesn't really seem to help that much compared to just using a single thread. But overall, I mean, if you're going away and running quite a long simulation, say, and yeah, you want to save time and save resources, then it's worthwhile looking into using this, because you can improve the performance a fair bit and then save on resources. But yeah, this is, again, you have to do the investigation first. So yeah, that's me finished. I don't know if there are any questions.
Yeah, if there are any questions, feel free to either speak up or write them in the chat, and then I can read them out.
Can you hear me?
Yeah.
Oh, hi, I am Federico. I would like to ask you a question on slide 27.
27, yeah.
Where you have LAMMPS 3 million.
Yeah.
This is something that I observed probably in another plot you have, but between 64 and 128 nodes, it looks like that the performance between the 2 and 4 threads reverse, as if something happened between 64 and 128 nodes that changed the performance of the 2 and 4 threads nodes threads case. Do you know why?
So I don't know why exactly. I did mention there was a bit of an issue with the IO on MPI on LAMMPS. So where, you know, basically having more processors writing was really hampering the write speed. So based on that, maybe if going from having more nodes and more processors, having 4 threads rather than 2 reduces the number of processors per node. So that might have helped in that case. But yeah, I don't know exactly, but because I haven't looked into that particular result, but it might be due to the issue with the IO.
Yeah, because I found it also in slide 25 for GROMACS.
Okay.
If you go here, yes, you see you have 16 and 32 nodes, and in both cases you have the 2 threads case is more performant on 32. I'm speaking about the 1.4 million particles. The 2 threads is more performant on 32, and the 4 thread is more performant on 16 nodes.
Yes, that's the other way around, I think. From
3 million is the other way around.
Yeah, from 3 million it's the other way around. Yeah, I don't know myself. I mean, there's a lot of factors. I mean, I'd have to go away and look at the profile more in depth.
I was just curious. Sorry for
the
tricky question.
I could probably find out, maybe take a look at profile in it. But yeah, what I did notice was scaling up the particle mesh UL calculations were becoming more and more significant. And then yeah, using multiple threads was helping with that. But yeah, I would have to take an in-depth look at the 2 particular results to work out what was happening exactly. But
thank you.
Question in the chat.
Yeah, so we have a question from George. Did you try assigning more threads per process than the recommended maximum to try to overspill the numeric region?
No, I've not actually looked at that. Yeah, I would assume the performance would be quite poor in that case. I mean, in looking at these results, when I've gone to 16 threads even, the performance is, you know, not great. It's probably, I don't think there's a single case where 16 threads is winning out on any of the others. So I don't expect, say, using 32 threads would be very good. But yeah, I haven't looked at it.
All right, so we have another question from Joshua Elliott. Are there any libraries available, so for example, ALPA on ARCHER2 to improve the performance of these codes?
So I don't think ELPA is available centrally. I did use ELPA in my build of CP2K, but yeah, but I don't have a version without it, so I can't maybe compare the effect of it. But it is possible for you to build your own version of ELPA and incorporate it within codes.
Any other questions? Yes, Sachin?
Yep.
Yeah. Hello. I would
Hi.
like to know, yeah, if you had, did you pin the threads to the NUMA region?
Yeah.
Okay. Okay.
Yeah. So yeah, it's set so that.
And did you also measure some L3 miss ratio, L3 cache miss ratio?
No, I didn't look into that. No. Yeah, that could be worth looking at.
Okay. And the last question is, did you look at WASP code?
So no, I didn't look at VASP. I had a quick look at it. I did try run it with MPI plus OpenMP, but I was finding issues with correctness with multiple threads.
Yeah,
so that's something
actually,
to
we
look
were also
into.
experiencing similar thing. Yeah.
Okay, yeah.
Yeah. Okay.
Any more questions?
Okay, I guess if there are no more questions, I should thank Holly for giving this webinar. Okay, there's another question from Stan. Are there standard Slim scripts available on Archer or on the ARCHER2 web pages to help with this?
Yes, yeah. So the example I took was from the documentation. And that, yeah, there's some information about choosing the right numbers of threads as well. Oh, thanks, Juan.
Yeah, I was just gonna go start, but that could have taken a while. Thank you. Okay, great. In that case, if there are no more questions this time around, thank Holly, and there will be another webinar tomorrow based on an ECSC project on fire drake. So if you guys are interested, feel free to show up. Again, it's going to be at 3 p.m. just as it was today. Thank you.
Thanks.